So when I'm working with this idea of a paired sample, the goal is that I want to relate group 1 to group 2 deliberately, whether that's the same person or whether it's some connection between the two groups and the individuals within them. And then I'm going to do these paired samples using what is effectively a one sample t-test by connecting these differences. So let's take a look. At a 0.05 significance, 5%, does this sample of 7 people, families, show that daughters are taller than their mothers? Daughter's height, mother's height. We're going to do this entire problem under the idea that now clearly I've got to pair these samples up. It doesn't make sense talking about the daughter from family 5 and the mother from family 1. I want to know the direct connection between this person and their mother. Okay. Let's think about the way we would set up hypothesis here. Are daughters taller than their mothers? So the data as listed provided to us in chapter 10's data files under the file titled height in the chapter 10 zip file that's on our Canvas page as a list of daughters' heights, list of mothers' heights. Let's define the difference. Now, before I go any further, a null hypothesis and an alternate hypothesis. The question I am asking at a significance of 0.05, are daughters taller than their mothers? Tells me this difference should be what for our alternate hypothesis? If I don't have a hypothesis, I can test all day long. I don't know what I'm testing. So what am I testing?
If the height is bigger than the daughters and the mothers.
Okay, but now how do I turn that into the difference idea? The difference between the two should be what kind of a number, if I'm right, and daughters are taller? A positive number. So my claim is that the average of the differences should be positive. That's my alternate hypothesis, that on average, we get a positive number because of this word right here. Now, this is the average for the differences, so I'm going to write mu sub d, as we see in the formula above. My null hypothesis is, no, there's really no difference. Either the daughters are not taller or the daughters are even a little shorter. This is a one-tail test. Since my alternate shows that this is a positive, I'm saying this is a right tail test. Okay, in order for me to get a critical value for my t, I need something important before I go on and look at the t-chart to tell me what the critical value is. What is the thing I need in order to be able to look at the t-chart?
The alpha.
I have the alpha,
The degree of freedom.
degrees of freedom. And for a one-tail test, degrees of freedom is
And -1.
number of samples minus 1. So I go back to my data over here. There are 7 families. My degrees of freedom is 6. So now, degrees of freedom at 0.05, I need a critical value. One tail test, 0.05, 6. There's my critical value. 1.943. With only 7 families, I could probably do all the rest of these calculations by hand. I'm not going to. Here's my height data. If I do this as a one-tail test, I need all the differences. So I subtract. Daughter's height minus mother's height. There's the difference column. I have a mean, I have a standard deviation, and I have a calculated t-value. And I get that calculated t-value using exactly the formula we expect. The one we had in our notes from Friday. The actual mean minus the expected mean divided by the standard deviation over the square root of the number of samples. Same one we used in chapter 9. So, here's my $64,000 question. Are daughter's heights larger than mother's heights? Do I reject the null hypothesis and take the alternate or not? The highlighted values are the ones that give me the answer to that question.
Yes.
Because
Positive.
the average difference is positive, because the average distance is 5.885, but that could be explained by statistical randomness, right? I need to know if there's chance that this happened by random is less than 0.05. That would be a p-value. I haven't done a p-value, but the other way I can check is if I'm in the rejection zone. How do I know whether or not I'm in the rejection zone?
You can check the p-value.
I haven't done the p-value yet, but how do I know just from the z-value, t-values? T, not z. From the t-values, how do I know whether or not I'm in the rejection zone?
we have to see T critical and critical.
which are right there.
I mean, T critical is bigger than T cal.
T critical is bigger than T cal. Am I in the rejection zone? There's a picture. You can't see that because I still have Excel showing. There's a picture. Where's the rejection zone for a one-tail test? The right tail test. So I need to know if the critical value is smaller than the calculated value. The calculated value has to be bigger for me to be in that little gray rejection zone there. What do I see up there?
It's more.
1.9299 against 1.943. I'm smaller. And that means I'm trying to make your lives easier by doing the work for you. But if you can't interpret what the computer spits out,
I mean, we don't have to reject.
I don't reject the null hypothesis. It's really a close call. But in this case, this evidence does not support the idea that daughters will be taller. Now, you see all that junk over there on the right-hand side? That's the result of doing this as a single calculation. From the data, I can go to data analysis, wrong data, this data, data analysis, and one of the tests down here says paired samples. So if I run that test, which is variable 1? Daughters was variable 1. Mothers was variable 2. And we are assuming the difference is 0. That was our mean expected difference. If they're not taller than, they could be exactly the same. Yes, I highlighted the words mother and daughter, so I'm going to click labels. And I'm going to ask it to spit this into an entire new worksheet. And it will generate for me a whole bunch of crap. This is where I get a p-value from. I could also get the p-value from my calculated t, but I need a computer to do that. I wouldn't be able to do it directly. This doesn't contain all of the t-table for me to be able to do that. This only contains the critical values. So, one tail, there's that t critical, 1.943, same one we came up with off the table. Our calculated value, 1.9299, that's t stacked. What's my p-value?
You can take the two-take p-value and divide it by 2.
I could, but I can also just take the one tail value right here, which is the same value I get as the 2 value below, divided in half. But that's 0.0509. What was my threshold? What was alpha? Son of, this is close. This is really close. 0.051 versus 0.05. If I just had one more family, maybe I'd get a different answer. If I'd chosen alpha equals 0.06 instead of 0.05, then I'd say we reject the null hypothesis. Look at how close a decision this is. Simply based on one value. This is really close. And now the textbook asks me two questions. It asks me, is the decision close? Well, hell yes. And then, why? Why might daughters tend to be taller than their mothers? Why might they not? That's a question that has nothing to do with the statistics. It only has to do with what you know about genetics and biology, right? It has nothing to do with the stats part anymore. So I can tell you, hey, this is not statistically significant enough for me to draw the conclusion that daughters are taller than the mothers. Why would there be evidence towards that? Why would you think daughters will be taller than their mothers? Women are getting taller over the history of time? Come on, people, talk to me. The answer is not tattooed on my forehead. I know my forehead's big enough. Come on. Why might you think this? Height is genetic, isn't it?
Because of the father, maybe.
Because of the father, maybe. And on average, men are taller than women. They might contribute, on average, to additional height. Maybe. Why might it not be related? Because there's too many other random variables that might change that. Genetics isn't perfect. If you want an example of this idea in practical terms, look up the idea of Lamarckian evolution. Reasons giraffes have long necks is because they kept having to stretch for big high leaves on the trees. They grew bigger necks. Now this is questions.
In the exam, how can we do it without?
Well, if I don't give you the output from this sort of thing, and I ask you to do this by hand, you should hit me with a stick.
So we will have this data.
I should hope so.
Okay.
And if you look at the review sheet, you'll see that in a lot of cases I did do that. So I don't expect you to generate most of this because it's long and tedious by hand. But could do this on my calculator in the same way, right? Let me get rid of the file we were just working on. Okay. Under my tests, I have a 2-sample t-test. And it just says pooled or not, right? Doesn't say anything about paired. So this is a problem when I go to do that here. But I thought there was a paired version. That's the Z1. Nope. I suppose if I were going to do this by hand on here, I do it as a 1-sample test. I just have to work out the differences first, right? So I'd have to go through and do that subtraction between daughter's heights and mother's heights, and then I could use this version. And my benchmark would be 0.
Could you potentially like do one for the daughters and then do one for the mothers and then compare those
Do one what?
t-test?
Okay, if I'm going to do a t-test, I've got to have a benchmark, right? So I'm going to say that the daughter's height is bigger than, oh, what's my benchmark? The mother's heights? But then that's really doing the comparative between the two, isn't it? I can do something between the two groups and then compare them for overlap. I could think about doing a confidence interval for the height of the daughters and a confidence interval for the height of the mothers. And if those two intervals overlap, then the daughters might not be taller than the mothers, right? So I could do something separately for each one. It's confidence interval. But I think I'm better off, since I deliberately want to pair them up, looking at it that way.
So the way you would do it on here is you would do you would calculate the difference between each one,
Yes,
and then just throw it into a list.
exactly. So I would go through and I would say, I had mother and daughter, right? So in this first reaction, I take daughter minus mother, I get -5. I do this one, I get daughter minus mother, I get +4. I get 19, right? I'll just build that list instead. And then I can do a t-test on that one
And
list.
my null. Or would just be 0.
Right, because I'm asking against benchmark that the daughter and the mother are the same.
Yeah.
And that's why, even with that, we wrote that null hypothesis right here, right? We were comparing to 0. The average difference should be 0. This is why a hypothesis is necessary before we do any calculations. If I don't know what I'm going to test for, I don't know which test to work out. We should do another. You want to talk about drug prices or swimming speed? Swimming. Problem 17. Coach told the swim team that times in 200-yard individual medley in the championships are typically more than ½ second faster than seed times going into the meet. In other words, when you get to the championships, you perform better. And his claim is by more than ½ second. At 5% significance, do these times in seconds for 26 male competitors support the coach's assertion? Do we believe that the individual medley times are more than ½ second faster than their seed times? So, do these times beat these times? I got a lot of data here. Again, problem 17, the file is labeled swimmers. I'm going to go pull the file up. That's the drug price one. Here's the swimmers. Bing. Okay. The claim is that the difference between times at the championship meet versus the times going into the meet, so preliminary results versus the seed results, should be bigger than, on average, bigger than what? Back to the coach's question.
Bigger than ½ second.
Bigger than ½ second. So, my alternate hypothesis should be that the average difference is bigger than 0.5, not 0. Just as back here, I wrote a null hypothesis, but it's centered on 0. This time, with my swim times, are they improved by ½ second? Now it's important to figure out which way I'm doing the difference. Because it says the data is faster than the seed time. So I'm going to think of the difference between my two data sets . Which one's variable 1, which one's variable 2, so I know which way to do the subtraction. Because I want the times to get better. Getting better in this case means getting smaller. So if I make the left column of data variable 1 and the right column of data variable 2, then seed minus preliminary should be a positive number. I want the times to go down. So variable 1 minus variable 2 should be bigger than 0.5. Seed minus prelim bigger than 0.5. Well, if this is my difference, then my alternate hypothesis should be that the difference is bigger than 0.5. And my null hypothesis should be no, there's really no difference. Or whatever that difference is, it's less than half a second. But that means I need to make sure I'm doing that difference in the particular order I want. Because if I did it in the other order, I'd get negative 0.5, right? My championship competition race versus the race I brought in before that, well, this one should be faster, my time should be negative. Okay. You'll notice I don't have an actual single column here of the differences. So if I wanted to do this on my calculator, I need to do all the subtractions. But if I'm in Excel already, let's use their paired t-test setup. Data, analysis, paired t-sample, variable 1. Oh, I need way more numbers than that. Variable 2. Need way more numbers than that. There we go. Hypothesized mean difference is now not 0. I think the time was improved by 0.5 seconds. Need to make sure I put the new difference in. I'm still doing 0.05. I'm going to put this output out in a new sheet. Does the data that we gathered for these 26 swimmers support the coach's claim that times have gone up at least half a second? Am I doing a one-tail or a two-tail test? Do a one-tail test. I just want to know if they went up. So I know which value to look at in that one tail. I want to look at the value that says one tail. There I've got a t-crit for one tail. And I've got a p-value for one tail. And I have a t-stat. So now you have two different ways of answering the question. So now I need the answer. Yes or no? Do we believe the coach times went up or not?
We believe that d is above 0.5.
I do believe it because
Because we reject the null hypothesis.
that p-value up there for one tail is 0.04. My sensitivity alpha was 0.05. The difference in swim behavior at the championship match is statistically significant above 0.5 seconds increase. The data does support the coach's assertion. I could also compare the two t-values, right? The t-critical is 1.708. T-critical for one tail. And my t-stat, my calculated t-value is 1.8. 1.821. Oh, it's bigger. 1.7 to 1.8. It's not a huge amount bigger, but it is bigger. There we go. Questions? So again, if I'm looking at connections between groups, I don't just want to randomly compare the two groups as wholes. If there's a specific relationship between them, I want to match them up. There might not be. I mean, we could be looking at two different fertilizer treatments for seed growth. We could be looking at people who took a particular weight loss medication and their weight loss behavior, and people who just went through an exercise regimen. So did this drug make a difference? Quite frequently, any sort of setup that has a control and an experimental group, those are the things we're going to see end up using these sorts of paired or unpaired tests. If I can do it for means, I can do it for proportions. Okay, wait a minute. This means I've got two population proportions. I go out and I do a sample. And I gather information from group one, I gather information from group two, I get a sample proportion from group one. This is again where I start to get upset at the fact that I'm going to use P for proportion and I'm going to use P for probability when I talk about P values. This pisses me off to no end, but I didn't write the book. So now I can think about my null hypothesis, my alternate hypothesis again. And I can say either there's no difference in the group, or there is a difference in the group. That means I'm going to have the same setup as I did before for my three versions of the test. Either my null hypothesis is, hey, these really are the same. My alternate is that they're different. Or what are my other two options? This is, they're the same or they're different. It doesn't tell me which direction the difference is. So this is a two-tailed test idea. What are my two one-tail versions?
Always better than equal to. And, each alternative is, no, less than.
And that will be a left, because we're off to the left side. And then the reverse over here. Now, I'm perfectly happy to think about this way. But I think it might be easier to do what we were just doing with our paired idea and look at the difference instead. So another way to look at these exact same three situations is to look at the difference. Same exact three sentences. Just all the pies are on one side. Left tail, two tail, right tail. And remember, I've got sample proportions for each group. So now I need to say, based on my sample, which of those hypotheses is going to hold. All right. Most of the time, when I'm thinking of proportions, I'm assuming. Remember what happens when you assume. Sometimes you make an ass out of you and me both. Assuming normality. If I am assuming normality, the minute I hear the word normal, what do I think in my head? Normal. Normal distribution, that means z-scores. So instead of doing t calculations for proportions, just like in the confidence intervals, just like in the one sample tests, whenever I do a proportion, I'm dealing with z-scores. Now that's a big if, that's why I've underlined it. We'll come back and we'll figure out when we have this idea and when we don't. If I'm doing a two-tail test, which is the most common one I'm going to do here, then I can do the same thing I did with the variances in the two-tail tests, and I can pool them. I'm going to get a combined proportion or a pooled proportion. I'll call it P sub C. In the pooled variance, we did SP squared, but I'm already using P. I don't want to do that again. So PC for combined. Remember, X1 is the number of yeses in group 1, X2 is the number of yeses in group 2, and N1 and N2 are the sample sizes for each of those groups. Again, this is not the same as just adding population proportion 1 and population proportion 2. Normally, I would say I would subtract the difference here, right? But we were talking about this being 0, so there is no difference for me to subtract. And then I divide by the standard error I'm dealing with proportions. The standard error is the ugly version of that formula. Big square root. PC times 1 minus PC times 1 over N1 plus 1 over N2. All of that is under the square root. Now, the advantage here is that this is a calculation that is substantially easier to do by hand. And the p-value is easier to do by hand because I have much more information for the normal distribution. I get the whole table for the normal distribution. I only get the critical values for the t-tables. This is z. I can do this a lot easier. Here's my example. Ready? Problem number 25. In 2022, a sample of 200 in-store shoppers showed that 66 paid by debit card. In 2023, a sample of the same size showed that 86 paid by debit card. Out of 200 shoppers in store, 66 paid with a debit card. The next year, out of 200 shoppers, 86 paid with a debit card. Has the proportion of shoppers changed sufficiently to be statistically significant at an alpha of 0.01? Now, I'm going to make the assumption of normality. I'm going to use this e-score here. After this, we'll talk about how you can check to see whether or not it's normal. But let's start with assuming it's normal. Means I need this. First question. What is the proportion in group 1? (2022) survey showed 66 people paid by debit card. What's the proportion?
66 divided by 200.
Or 0.33. How about in 2023?
86 divided by 200.
Or 0.43. So the number went 10% higher. Is this statistically significant at a sensitivity of 0.01. Again, assuming normality, assuming my difference was 0, I'm going to pool these. What is my pooled variance? Sorry, pooled proportion.
Point 38.
Now I can do this calculation. P1 minus P2, 0.33 minus 0.43 over big square root. PC, 0.38, 1 minus 0.38. (38 from 100 is 62. And then 1 over 200 plus 1 over 200. Okay. I need a value. Out come the calculators. Now here's the question for you. I have not yet created a critical value or a p-value. I need one of those two to answer the question. If you want the p-value, you're going to find p that z is less than negative 2.06. And 2.06 is on my chart here. 2.06. The other thing I could look for is the critical value for 0.01. But you already wrote that one down. What's the critical value for 0.01? 1 tail or 2, you can do it either way. But I don't need that. This p-value right here, do I accept or reject my null hypothesis? Oh, it's off the top of the screen. If alpha is 0.01, this p-value is bigger than that, I should not reject. I'm not in the rejection zone. If I'm not in the rejection zone, I need to support the null hypothesis. There has been a change. It is not statistically significant. Okay. On Wednesday, we'll talk about when am I allowed to assume normal behavior. Because I made that assumption Nobody called me on it, so we should figure out whether or not I was right or if I screwed up here. I will see you all on Wednesday. Have a wonderful rest of your day.